Hello, this is AMET 104 lecture recording week 9.1. So up until last class, we went over chapter 15, and that is actually all done. So today we're going to go into chapter 16, and the chapter 16 is probabilities, odds, and expectations. And the first section, 16.1, is sample space and events. So this chapter doesn't really have any, 16.1 does not really have any heavy computations. It's more of identifying and understanding the whole concept. So we're going to spend some time going over some definitions and looking at different examples today. So the first definition we want to look at is the random experiment. So what does it mean by random? So the random experiment means an activity or process whose outcome cannot be predicted ahead of time. So, for example, we have tossing a coin. And we have rolling a pair of dice. Drawing cards. What else? We can also predict, so it's predicting a football game. So predicting the result of a football game. And we can also forecasting the path of a hurricane. And there are many more. Anything that's not certain, something that you cannot certainly predict what is going to happen. Yes, we can, with different data, we can somehow forecast what's going to happen. We can predict what's going to happen, but we don't know if that's actually going to happen. It's like a when we look at the weather forecast, it will tell you that when it's going to rain, when it's going to be sunny and everything, but it's not always correct. That's why it's what we were saying, it's not predictable. So random experiment simply said it's something that you cannot like precisely predict the outcome. And let's look at the next definition, is the sample space. So the sample space is a set of all of its possible outcomes. So that's pretty simple, and it's often denoted as capital S. And here we will denote the letter, capital N in this case, as, sorry, we'll use the letter, sorry, that wasn't the correct terminology. We'll use the letter N to denote the size of the sample space. So what does that mean? So what do you mean by size? We've already talked about this in chapter 15. Size means the number of elements or number of data points in the data set. Here, sample space is also a set. It's a set. So it means that when you're denoting sample spaces, we have to use this curly braces that we would use, and you would lay out the outcomes here with the comma. And since it's a set, there are elements. So it's, think of it as a data set and data points in the set. So, so when you say the size, it means the number of outcomes in S, in the sample space. So it's the same concept. So let's actually look at an example. So we said the one of the most common examples that we use for the random experiment is tossing a coin. So let's do that example. So let's toss a coin. And that is a random experiment. Then what's the possible sample size? Sample space. So the sample space, you can either say, if you want to look at the outcome, so let's say this is the possible outcome will be, let's say, heads or tails. And that's it. There's no other possibilities. That's the only possible outcomes that you can have. So the sample space would be heads or tails. Here I'm going to denote H and T. We can also look at it in a different way. We can also look at it, instead of specifically looking at the outcomes like heads or tail, let's say we were playing a game. So if we were playing a game, and let's say if you get heads, you get 1 point. If you get tails, you don't get any point. Then you can also say the sample size in this scenario will be either you get no point or you get 1 point. Meaning if you get a tail, you do not get any points. If you get heads, you get a point. So the sample space is all dependent on how you define the space itself. So in the first case, we only looked at the actual outcomes, heads or tails. And the second example, we were doing it as if we were playing a game, and you get a point if you receive a head. If you you don't get any points if you get a T, the tail. Let's do a little bit of a bigger example. How about tossing 2 coins? What about tossing a coin twice? So if you were just to look at the actual outcomes, what would be the possible outcomes? So we can first get heads, and for the second toss we can also get heads, and that's a possible outcome. So this means that this is the first toss, this is the second toss, and we're denoting HH as the heads. The first outcome was the heads, second outcome was also heads. We can get the heads for the first, but we could also end up with the tails in the second. And the reverse could also happen. We can get the tails in the first and get heads in the second. And lastly, we could also get 2 tails. And there are no other possibilities in this case. So here we can also see that when you're tossing a coin twice, the sample space is as such, as how I just wrote down. But what if we were more interested in the score? Let's look at the score outcome instead of the actual outcome. So suppose you're getting a point if you get heads, you do not get any point if you get tails. Then the first one, obviously you get 2 heads, so you get 2 points. The second one, you get heads in the first, but do not get any points in the second, so it's 1. For the third one, it's the same way. You don't get any points in the first row, but for the second toss, you do get a point, so it's 1. And lastly, you don't get any points because you didn't get any heads, 0. But one thing that's important is that now we have 2 ones. Even though those ones came from different outcomes, different, these ones came from different outcomes. At the end, when we're really talking about a sample size, sample space, it's still the same. This 1 point is no greater than this 1 point, and they're actually the same. So in this case, when we have the repeating outcome, we're simply redacting 1 and just put 1, 1, and it's going to be like this. Let's do one more example. Let's do tossing a coin 3 times. So this can be a little tricky, but if you follow your own logic, it should be simple. Simply, you can get 3 heads. You can get heads for the first 2 throws, but end up with a tail for the last one. You can also get heads, tail, heads, tail, tail. And those are all the outcomes that's possible when you, with the first outcome as heads. So now we're moving on to the tails. So tails, heads, heads, tails, heads, tail, 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 heads, and lastly, we can get tail, tail, tail. So the important thing to look at is here, so we get 3 points here, 2 points. So these are equivalent to number of heads. 2, 1, 2, 1, 1, 0. As we can see that there are a lot of repeating numbers, and when we're talking about the score outcomes, we don't really have to include every single one of them. So we can see that 3 is possible. So 3 is an outcome, and 2 is an outcome, 1 is an outcome, and 0 is an outcome. And that's all it is. So here, one last thing I want to note here is that a sample size. So the size of the sample in this case, obviously it's, I wish I had more space here. So size of the sample, I'm only going to talk about the left ones, the actual outcomes. So the size, n is 2. And here we can see the size is 4. And lastly, here we can see that the size is 8. So do we see any patterns? Do we see any patterns in terms of these numbers? We've already went over sequence, and this is a sequence actually. So we can see that when there is 1 coin, this is simply 2 to the power of 1. And when there are 2 coins, it's 2 to the power of 2. When there's 3 coins, it's 2 to the power of 3. So 8 is 2 to the power of 3. So this is actually the total number of outcomes. In other words, the size of the sample. So we do not have to actually search. We don't actually have to compute how many outcomes will there be when there are 4. When you're tossing a coin 4 times or 5 times, 6 times, doesn't matter. You can simply increase this exponent. So this implies that tossing a coin 4 times implies that the n is 2 to the power of 4, and this 4 came from this 4 times. And simply, this is 16. So here, the bottom 2, the 2 down here represents for each event, you can either have heads or tail for each toss. And the top 4 represents how many coins there are. So yeah, that's it. That's really all you're looking at when it comes to computing the number of outcomes, or in other words, the size. Let's now look at an example where we deal with something more applicable to real life. Example, let's say in a penalty situation, a basketball player shoots 2 free throws. And then the sample space is simply, if you're denoting the success as the S, and if you denote the failure as F, we can say that this specific player would get success, success, or success, failure, failure, success, and failure, failure. And those are the only outcomes. And these are actually the same as tossing a coin twice, and we can all see that. So that's a sample space, but oftentimes in sport matches like basketball game, you would be more interested in the possible score gain. So the sample space for the possible score gain is, in this case, if you score both of them, it'll be 2. So the free throws only count for 1 point per throw. Sorry, 1.4. Do you call it a goal? I'm not really familiar with the basketball terms. So if you score both of them, you end up with 2 points. If you score the first one but do not score the second one, it'll be 1, and vice versa. You score on the second but not the first, would also be 1. And if you don't score anything, it'll be 0. So we can see that the possible score gain is you can either gain 2 points, 1 point, or nothing. So those are the 2 different types of sample space that we can speak of in this scenario. And in a 1-and-1 situation, the player gets to shoot the second free throw only if he makes the first one. So in other words, if the first one is not a goal, if the first one is not scored, the player doesn't get to shoot the second one. Then the sample space in this case would be, if you score the first one, then you have a second choice, which you can end up with another goal. You could also end up with the first goal, but ended up not scoring the second one. And lastly, you can simply miss your first chance and don't get the second chance at all. And those are the actually only possible outcomes. And lastly, the score gain would be, if you score both of them, it's going to be 2 points. If you score 1, it'll be 1 point. If you don't score at all, it'll be 0. So it's 2, 1, 0. Let's do one more example on the sample space. Another very popular examples that we use is rolling dice. Rolling a die, obviously, it's very simple. If you're rolling one die, we have 6 outcomes. We have 1, 2, 3, 4, 5, and 6. But it gets quite confusing when we're rolling more than one die. So, for example, in this case, let's look at the rolling a pair of dice. So in an order pair, we're going to say so express in ordered pair, meaning first outcome and second outcome, like this. This means that for the sample space, we have, you can get 1 for the first roll and 1 again for the first roll. You can get 1, 2. You can get 1, 3, 1, 4, 1, 5, 1, 6. And now we're all done with the first roll being 1. So with the first roll being 1, we can either get 1, 2, 3, 4, 5, 6 for the second roll. And now we move on to this first roll being 2. And we will continue this all the way up to when it's 6 and 6. And we can also see that in this case, the possible scores, if you are counting each face that we get after rolling as scores, we can simply add the 2 each. And this is going to be the smallest that we can get is 2. You cannot get 1 or 0. You can get 3, 4, 5, 6, 7, 8, 9, 10, 11, and the largest score we can get is 12. So what about the size? So in this case, for this whole thing, the size n is how many, so it basically tells you how many outcomes can there be when we're rolling a pair of dice. You can simply say that you can either get 6 different outcomes for either, and this is simply 6 squared. So we have 6 different outcomes for each die, and we have 2 dice, hence this is 36. So if you actually lay out every single one of these outcomes, you will end up with 36 different outcomes. So here, when we're saying it's order pair, it means that the order matters. So a lot of you may think that rolling 1 and 2 is the same as 2 and 1. And a lot of the cases, if you're playing a game by rolling a die or rolling a pair of dice, when you're more interested in the score, that's true, and that is what we're looking at it down here. But when you are looking at all the possible outcomes and expressing it in order of pairs, it means that the getting 1 and 2 is not the same as getting 2 and 1. So they're actually 2 different things. So so I think that's really all there is to it in terms of the random experiment and sample space. Let's now look at the different definition. So the new definition we want to look at is the event. An event is a subset of the sample space. And any subset of the sample space can be considered an event. So obviously, by definition, we can see that events are sets, so we still use the squirrely braces here. So let's just look at an example. Let's do a simple example when we're tossing a coin twice. So example, because these are small enough that we can actually work with, but it's not too small. Tossing a coin twice. So obviously we have seen in the previous example, when you're tossing a coin twice, we can either get heads, 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 tail, tail, heads, or tail, tail. And that's the sample size. Sorry, sample space. Then in this case, we can make different events. So let's talk about a few events. So let's say, for example, actually, instead of going it that way, let's start this like this. So what about, there's this thing called the empty set. Is considered an event. And essentially, an event with no outcomes. And this may look a little weird, and we often call this an impossible event. And in this case, we often say that we often denote it as the squirrely braces, but with nothing in it. And for example, in this case, tossing 3 tails. So that'll be an example. So this doesn't make any sense. We're tossing a coin twice, but how would you get a tail 3 times? And that's exactly the point. It's not possible. And if you see something like that, we can see that this is an impossible event. and we denote it as such. So that's it. And we also consider this an outcome. We consider this an event. Even though it may be very weird and trivial, we still call it an event. Another thing that's worth noting is the entire space. S is an event. And we usually call this a certain event. So we can obviously, in this example, let's say simply just tossing heads or tails. It doesn't really matter. In this case, all the events that we have, I mean, all different outcomes that we can have heads or tails in it. So simply, this is the entire space. And we often just call this just the S as the sample space. The another events that we have, so events in this case, heads, tail, heads, tail. In other words, the events that only consist of one outcome. So consist of one outcome. And is called a simple event. And that makes sense. And a few more examples will be, we can say first and second toss is the same, are the same, sorry. Then we can say this is heads or tail. If we say the same thing, are different. That was a little weird. Are different. Then obviously this is heads, tails, or tail heads. Let's say what else? We can also say something like at least one tail, and we can simply say that heads, tail, heads, tail, and that's at least one tail. And there's also, let's say, first toss is heads. Then that is heads, tail, and that's it. So all these words, these are all the examples. There's no set term how you can describe it. You can describe it in many different ways. And the whole point of this event is to understand how many different events there are and what kind of events do fit in that description. And there is that. So there's really no set method how you want to go about showing all these different events. Hence why I was it was kind of tricky for me to explain what this is. But I think more examples, more solid examples may make it a little easier. So I think I'm going to end the class here today. I think that was enough content for chapter 16.1. Next class, I will go over some examples, a few examples that you can see on homework examples or quizzes or exams. And hopefully after then, all these definitions and examples will make more sense to you. Thank you for joining the class, and I hope you have a great rest of the day.